All right, so we're going to continue in relating mixing time to diameter and then go on to relate to the handout and discuss the connection of mixing times to hitting times of large sets. But first, something about, still about rate of escape. So, okay, so before I discussed the lower bound for the distance traveled, I'm sorry, an upper bound for distance traveled in terms of diameter. Now I want lower bounds. And these will require an additional assumption. So the theorem I want to prove now, which is in a joint paper you can find on the archive with James Lee, is the following. So we're going to take a G, a transitive graph. And it means all vertices look the same. And then we'll have two cases. One in the case when G is finite, and the other is the case that G is infinite and G is amenable. And let me recall that G amenable, what it means is you can find some Fellner sets. You can find some sets AN in the graph, which are finite sets. And if you look at the size of the boundary of AN, so how many edges connect AN to its complement, and compare to the size of AN itself, this goes to 0 as n tends to infinity. Okay, so a graph or a group is amenable. This is not the original definition, but it's equivalent in our setting. If so. So for a transitive graph, the definition we're using is amenability means there exist sets where the boundary compared to the size of the set is arbitrarily small. There's some resonance here. So again, the boundary of AN is the set of edges that connect AN to its complement. And we want that this set of edges is small compared to the size of AN itself. So the standard example of an amenable graph is ZD, the standard lattice, where large boxes have this property, while a standard example of non-amenable is, say, a regular tree. But there are many more examples. So for G, these are the two cases I want to consider here. And then in this infinite case, the statement is very simple. The distance squared from x0 to xt, again, this is the graph distance, is going to be bigger than t over d. So d is the degree here. And the degree does not change between one vertex and the other because the graph is transitive. And for G finite, I want to make the same statement. So I lose a constant, lose d, but of course, so I want that the distance squared will grow linearly. Well, it can't do that forever. And the interesting open problem is how long can we guarantee such an inequality? What we can prove is for all t less than the so-called relaxation time. So remember, our random walk matrix, transition matrix, had a leading eigenvalue of 1, and the second eigenvalue we call lambda 2. The difference between them is an important quantity called the spectral gap. And the inverse spectral gap is often called the relaxation time. Okay, is this hard to see? There's some problem with the light, maybe. So for all times which are less than the relaxation time, the distance squared is bigger than t over 2d. So, so it should say that even though these statements look kind of simple, and you'll see the proof is quite simple, this is statements that we didn't know for a long time. And the breakthrough idea came from Anna Oeschler in 2005, and in the context of infinite groups. So one question that people working on random walks on groups did not know is, take an infinite group, finitely generated, look at the simple random walk and the Cayley graph of the group. How slow could it go? So it's natural to assume that the integers is the slowest group, and then the distance squared grows linearly. But all the heat kernel estimates we knew, all the transition kernel estimates we knew, which were very sophisticated, for instance, due to Veropoulos and his co-authors, they only gave that the expected distance grew like t to the 1/3, so expected distance squared grew like t to the 2/3, and they didn't give us this linear growth of the expected distance squared, and we still don't know to derive it from heat kernel or from transition probability estimates. And the new idea that Anna contributed is that one should derive this kind of estimate by an embedding idea. One should take the group and embed it into Hilbert space. And there was available a theorem by Mok that says if you have an infinite amenable group, there is a harmonic equivariant mapping into Hilbert space. I'm not going to go into the exact definitions here, but this is a Lipschitz mapping of the group into Hilbert space. So from the group graph metric in the group to, in the Cayley graph, to the norm in Hilbert space, which is Lipschitz, and no, it can't be quite be by Lipschitz, but for any vertex, one of its neighbors has a large norm in the difference. So I'm not going to go to the exact definition of the Mok theorem, but I'll just mention for those interested that there is an exposition of this in the appendix of a paper by Kleiner. So Bruce Kleiner has a very nice paper from a few years ago on a new proof of Gromov's theorem on groups of polynomial growth. And in the appendix, he proves Mok's theorem. This proof is based on ultrafilters. And so after Anna suggested this, then we basically knew this kind of statement for amenable groups by the path she suggested, but the people working on random walks on groups, were very mystified by this Mok theorem. And so James and I sought to find a more elementary explanation, but still based on embedding ideas, and this is what I want to show you. So, in particular, the finite version of this is really completely elementary. In the infinite, you still have to say something, but it's still completely self-contained. And in particular, you can find our paper also on the archive, which discusses all this. But okay, let me start towards the proof. But maybe before the proof, let me say, and I'll say it again, the big open question is how far can you extend this? For instance, does this inequality hold, maybe with a different constant, until the mixing time? Does it hold until the diameter squared of the group? We don't know that. All we know is to prove it until this relaxation time. Okay. So let's prove this. We'll see it's easy, but using an embedding idea. So instead of this, let me get there. Instead of this, maybe one more comment about the infinite case. So in the infinite case, I made this assumption that G is amenable. Now, if G is non-amenable, then actually we know that the expected distance grows linearly. It follows from a theorem of Kesten that the expected distance grows linearly. So of course, by Cauchy-Schwarz, the expected distance squares grows at least like t squared. So we get something much stronger than this. However, notice that we get this, it's only stronger asymptotically. So one thing that I'm still embarrassed that we don't know even in the infinite cases, does this inequality as stated hold for all finitely generated groups? Does it hold for all Cayley graphs? We know it for large T. As I said, we know it for amenable groups. We even know it for groups with Kashdan property T, but we don't know it for we know it for groups without Kashdan property T. We don't know it for groups with Kashdan property T. I'm not going to define that because this is somehow beyond the scope, but that's a comment for experts. And now I'm going to, okay, now I'm going to erase this and state the key lemma we're going to use. So the lemma allows us to bound the speed in terms of the Dirichlet form. So I want to use this notation. What is the Dirichlet form at time t for a function f? So this is the inner product I minus p to the t f times f. Now here we're in the transitive case, so the background measure is just uniform, and it won't, the scaling of the measure won't matter. It's convenient just to think of counting measures, so don't normalize, just think of the scalar product is just with respect to counting measures, so you just sum this. Okay, so this is certainly defined for functions f in L2, in little L2. And then the statement is that if I look at the expected distance squared from x0 to xt, this is always at least 1 over d times this Dirichlet form at time t divided by the Dirichlet form at time 1. Okay, and you'll see this lemma has a 2-line proof. It will be easy, but before we prove the lemma, let's first apply it. Okay, so f is any function. Okay, so it's R, so we can choose the function here. And for any function, that's a good, very good question, thanks. The left-hand side has no f. So the statement is, for any function f in L2, we get this inequality. Of course, to get something meaningful, the denominator should not be 0. So the function, but the denominator is, okay. So we'll want to apply it for functions, which are not harmonic, where d1f, we want d1f to be non-zero, and then and that just means, as we'll see, that just means that f is not constant. Okay, so for any non-constant f, this gives you a bound, and later, of course, we'll want to optimize this bound. All right, so let's first prove. Let's apply this. So this is for finite or infinite. Let's apply this for finite g. For finite g, there's a clear optimal choice of what f you want to use, which is the leading eigenfunction. And indeed, it's an exercise to show that this function will really give you the best result if you want to apply the lemma. Now, it doesn't mean that the bound on the lemma is the optimal one for this. But if you want to apply the lemma, the best choice of f is this. And once we plug in this, we can immediately read off what we'll get, because what is, so let's choose F to be normalized in L2. So what is this? This is 1 minus lambda to the t over 1 minus lambda. Right? That's all we have when we compute this Dirichlet form. So this is just the series and okay, and remember we assume that t is less than 1 over 1 minus lambda, which means that lambda is bigger than 1 minus 1 over t. So we can write it like this. And just to be completely explicit, we get that, which is bigger than t over 2. Okay, and you can improve the constant a little bit, but I don't care about that. So, all right, so you get the t over 2. So if you just divide by d and use the lemma, you get the statement here. Okay, so for G finite, the lemma immediately gives you the statement. And okay, we'll prove the lemma in a moment, but what do you do for G infinite? So it won't. So G amenable exactly means that the spectrum the spectrum has accumulation point at 1, and one can follow the same idea using the spectral theorem and suitable spectral projections. Alternatively, in the infinite case, one can use a function f of the form sum p to the L indicator of A. Either a finite or an infinite sum. So you take A to be one of these Fellner sets, and then you look at this sum which measures, so f of x measures with the expected time that the random walk will spend in A up to time L, and if you plug these kind of functions into the lemma, you'll get the statement in the infinite case. There's some more work in that, so I'm not going to do that right now, but you can find that in the paper. Okay, so let's prove the lemma, and you'll see this is completely elementary. If you'll open the paper, you'll find not everything there is elementary, but I'm shielding you from the more technical bits. So how do we prove the lemma? It's again an embedding idea. So we define a function f which goes from G to little L2 of G. Oh, I should say I'm going to prove the lemma. Okay, I should say that. I'll focus on the case of G, a Cayley graph. So what do I mean by that? We have, so this works for any transitive graph, but there's some more averaging work to do there. So the Cayley graph case is simpler. So you have a group, in our case, right, a finite or infinite group. You have a finite symmetric set of generators, S, and G is generated by this set. And the Cayley graph is just the graph where the nodes are the elements of the group, and we connect to if the ratio is an element of the generating set. Now, because this is a non-commutative setting, we have to say where we multiply. So this will be the right Cayley graph. So y is a neighbor of x will mean that y is in x times the generator set. And so we multiply on generators from the right, and then the random walk here will be on this Cayley graph. So it's obtained by starting at a group element and multiplying by a random generator from the right. Okay, and then another random generator from the right, and so on. That's the graph we're taking. Now, the function capital F will be defined by multiplying from the left. So f of x will be little f of gx as g ranges over g. Okay, so the group acts on the Cayley graph just by multiplication here from the left. So capital F is a mapping from G to L2 of G. Now, let's calculate for any choice of x0. It turns out the choice of x0 won't matter. What is the expected norm of f of x0 minus f of xt? Expected norm squared, where this is the random walk on the right Cayley graph. So we choose some x0. You can think of x0 the identity. It won't matter. And then we run this random walk on the right Cayley graph, just choosing an element at random. And I want to calculate what's this expected norm squared. Well, let's write out this norm squared. It's the sum over g of f of gx0 minus f of gxt squared. Okay, now let's write out the expectation explicitly. So whatever x0 is, as g ranges over the group, gx0 ranges over the group. So we have the sum over x. Well, let me write and then explain sum over x, sum over y. F of x minus f of y squared p to the t of xy. Okay, because this is, if we call this point x, then x ranges over the whole group. This point gxt I want to call y, and y is just the point you reach after t steps of the walk. So just writing out this expectation, you'll get this expression. And this is familiar as an alternative form for the Dirichlet form, up to a factor of 2. So you see that by expanding out the square here. So this is f of x squared plus f of y squared minus 2fxy minus 2fxfy. And because we are in the symmetric case, so the transition matrix is completely symmetric here. Pxy is just 1 over d if xy are neighbors. Ptxy is symmetric. So this, when you sum over the contribution, when you sum over fx squared times ptxy or fy squared times ptxy, these sums will give you exactly the same. So overall you get, I'll continue here, that this expression here is just equal to twice I minus p to the t f inner product with f. You see, so the f inner product with f is what we get, say, from this fx squared term, because if you take fx squared sum over y, you'll just get that. And what we get from the cross term fx fy will just be this p to the tf multiplied by f. This is, so we just got twice the Dirichlet form at time t of f. Okay, in particular, applying this at time 1, what can we infer? So what we want to infer is that if we have 2 points x and y which are neighbors, in the group, then if I look at 1 over d, f of x minus f of y, this norm squared, well, observe that this is less than the expectation fx0 minus fx1 squared, because it's just one of the summands in this expectation, which by what we calculated is at most 2 dt of f, 2 d1 of f. So for neighbors x and y, so multiply by d, take square root, and you see, so we get a bound on how far could fx and fy be for neighbors x and y, and this implies that the Lipschitz constant of f is at most square root of 2 d d1 of f. Okay, because f is a mapping from a graph to the Hilbert space, once we control how far f could fluctuate on neighbors, then if we have any two nodes, how far could f differ from these two nodes? We just look at the shortest path, and we see that it could differ at most by their distance in the graph times this quantity. So the Lipschitz constant of f just means, how far could fx and fz differ as a multiple of the distance of x and z. So because we're using the graph metric, once we controlled the distance between neighbors, we control the Lipschitz constant. And now we were just going to plug it in this calculation here. So in the calculation here, let's start that calculation from the other side and say we know that 2 dt of f is equal to the expectation of fx0 minus fxt squared. This itself is less than the Lipschitz constant of f squared multiplied by the expectation of the distance squared. Right? Because, of course, the distance difference between f at 2 points is bounded by the Lipschitz constant times the distance of those 2 points. So we just wrote down that inequality and squared it and took out the constant outside the expectation. Okay, but the Lipschitz constant we know, so we get here the Lipschitz squared, right? So here we get 2d times d1 of f. And now just comparing the two sides, we have the inequality we want. The expected distance squared is at least the ratio dt over d1 divided by d. Okay, so it's completely elementary, but it's still based on taking our group and embedding it into a Hilbert space and using the Lipschitz constant of that embedding. Okay, but everything is completely elementary. Any questions about this? Okay, but now as you'll find in the paper, and I won't go into here, by taking in the infinite case, by taking suitable limits of these embeddings, one can recover this mock embedding theorem again in an elementary way and get a harmonic mapping into Hilbert space. And then looking at this harmonic mapping along the random walk, you get a martingale in Hilbert space, and you can use martingale inequalities to get more information about the random walk. And I'm going to skip that and refer you to the paper for more details of that. So if there are no questions, I'm going to switch to my second topic for this afternoon. Okay, so I remind you that I have a question for you, which is, how long does this inequality hold? And let me point out that even that the case that we proved already has some implication. So let me write the implication up here. So look at this inequality for the finite case, and let's call this number the relaxation time, t sub sub REL, T sub relaxation. So now, if we look at this quantity here, the expected distance squared, well, it's certainly at most the diameter squared. So the diameter squared of G, I'll just write it as D squared, it's greater than T, and let's plug in the largest T that we're allowed to, which is this relaxation time, the inverse spectral gap, divided by 2D. Okay, so we get an inequality which was actually already known by different methods due to Babai, Jerome Sinclair. That says the relaxation time on any group and on any transitive graph, the relaxation time for the random walk is bounded by the diameter squared times twice the degree. Okay, so we contrast that with the lower bound we got earlier today, which is on any graph, which we got a lower bound for the mixing time of the diameter squared divided by constant log n. Now, there is a well-known inequality standard. I won't go into it, that the mixing time is always bounded up to a constant by a constant like 2, doesn't matter, times the relaxation time, but times the log n. Okay, so combining these things, you get that we know that the mixing time so combining these, so the bound with the, and again, n is just the size of the group, so combining these, we get that the mixing time is bounded by the diameter squared, well, times, okay, I'm going to ignore the constant out front, so times the degree, times the log n, or I'll write it as log the size of G. And here's my challenge to you, decide if we can remove this log G in the inequality. So of course, in general, this log G might be there, but in this general inequality, you need the log. But in this inequality, I conjecture that the mixing time on any group is always bounded by a constant times the degree times the diameter squared, or in any transitive graph. Finite transitive graph. But these methods only give it, and all the known methods only give it up to this extra factor of log, the size of the group. And since we're interested in very large groups, this log G is not negligible. All right. So you see here the transition between elementary bounds that take a few lines and open questions. All right. No more questions. I move to second topic, which is relating mixing times to hitting times. So the mixing time is the time where, for any substantial set, the probability the random walk is in it should be close to the stationary probability. On the other hand, the hitting time is, well, the expected time to be in the set, but it just refers to the time we are in the set once. So how are these related? So you have the theorem I want to show you today. I'll show you most of it. So the theorem just says that, okay, for reversible and lazy chains. So lazy chain is just a way to get rid of periodicity problems. So lazy chain, I just mean that the probability to stay in place is always at least a half. The mixing time is equivalent to the hitting time. So I'll write TH of 1/8. And what is this quantity? So TH 1/8 is the maximum over all initial states x and sets A where the stationary measure is bigger than 1/8 of the expected time starting from x to hit A. So by this symbol, I mean that these two quantities are equivalent up to universal constants. So there are universal constants that don't depend on anything that bound the ratio between these two quantities. I mean, they don't depend on anything because I put 1/8 here. In general, this kind of thing will be true. You can replace 1/8 here by any alpha less than a half, and the constant will depend on alpha. Okay, so this is a theorem. So this theorem was proved jointly with Perlasusi from Cambridge, but actually the same theorem was proved independently by Roberto Oliveira. Okay, he worked in continuous time, but it's essentially equivalent, and all of this happened last year. And you can find both papers on the archive. Okay, now I'll prove to you somehow the new part of this theorem. Let me say that there are two inequalities here. One is almost trivial. So the fact that TH so remember, T mix we define with a quarter. This choice of these constants are arbitrarily. This fact that TH of 1/8 is less than a constant T mix, this is very easy. So intuitively, obviously, in order to mix, you have to hit any substantially large set. And okay, so let's quickly see why this is true. So one comment before I go to that about this laziness assumption. This is just something to get rid of periodicity. For any chain, you can always make it lazy by averaging the transition matrix P with the identity. In other words, at every state, if you have a chain which is not lazy, maybe it's a bipartite graph, so it could be periodic, you get rid of that by each time tossing a fair coin, and if it falls heads, you move. If it falls tails, you stay in place. So that's why this laziness is just a kind of convenient technical assumption that you easily get. So all right, so TH 1/8 is less than CT mix. This is very easy. And the reason is take T to be a T mix, but of a different constant, say of 1/16, which it's an easy exercise that this is bounded by 3 times T mix. So remember, the definition of T mix was a T mix of a quarter. So if I look at T mix of 1/16, I want to get 1/16 close. This is, I just have to wait, say at most 3 times the mixing time for a quarter. So this is an easy exercise. It follows from the inequality that the distance to stationary at time t plus s is bounded by twice the distance at time t times the distance at times s. So we take t to be this time. All right, and now we want to bound TH of 1/8. So suppose A is a set where pi of A is bigger than 1/8. Then, using this definition of T, we can say Pt of XA This has to be bigger than 1 over 16 for all x. Because it has to be bigger than pi of a minus 1 over 16, which is 1 over 16. So we have the information that for any starting point x, at time t, we're going to be in a with probability at least 1 over 16, and where t is this quantity here. Okay, so now we're basically done because we can bound the heating time of the set A by t times, so it's stochastically dominated by t times a geometric variable with parameter 1 over 16. In other words, we can perform experiments starting wherever we are, run for time t, with probability 1 over 16 you're in A. If not, wherever you are, start another experiment with probability 1 over 16 you're in A, and so on. So the expected number of experiments you'll need to take is at most 16. So you get that the expectation of tau A is bounded by 16t, which is at most 48 t mix. So this bound is almost immediate. Okay, bounding the heating time by the mixing time. The other direction is not immediate, and it will be our next goal. So the proof actually of the non-trivial direction goes through several other notions of mixing that I've summarized in the handout for you. So the mixing time is actually equivalent to the stopping time, which is equivalent to Tg, which is equivalent to Th of 1/8. And I'm going to, so we know what T mix is, we know what is this, what are the intermediate quantities here. So T stop is the minimum, well, maximum over starting states of the minimum of the expectation of a stopping time where at that stopping time, the chain has exactly the stationary distribution. And I'll talk about some such stopping times later. So this is some other mixing notion where we stop at a random time and we want to hit the stationary distribution exactly. And Tg is a quantity we'll talk about now. So this is very close to the mixing time in its definition, but it involves stopping not at time t exactly, but at a geometric time of mean t. So it's the first time t, so that for any starting point x, if we look at, we start from x, and we stop the chain at time zt, and we look at this measure, compare it to pi, distance is less than a quarter, where zt is a geometric variable with mean t, so it has parameter 1 over t. This is a geometric that starts at 1, right? It has right, so the minimum value is 1, and you get 1 over t times 1 minus 1 over t to the k minus 1. So that kind of geometric variable. And all right. So This is this notion of TG. So the idea is instead of running the chain and stopping it at time t, we're going to, at every step, stop with probability 1 over t. So the expected time will stop is t, but the time will actually stop is random. And then we're going to look, but it's random independent of the chain. Right? So zt is this geometric variable completely independent of the chain. It's just a way to smooth the time that we are stopping. So maybe anomalies that occur at a specific time disappear. Now, so what I'll prove to you in the remaining time is mainly this equivalence, which is really the new result. These kind of equivalences, although they're non-trivial, they basically follow from, so this one is explicitly in an old paper of David Aldous from 82, and this one follows ideas of Lovas and Winkler from 95. But this one, but all of these are somehow mixing notions. They relate to being close to the stationary distribution, while this one relates a mixing notion to a hitting notion. Still, you'll see the proof, won't be hard. Any questions so far? All right. So, all right. So here again, this equivalence. There are two inequalities. One is easy, and I won't do it. It's like the one we just saw. So it's always easy to bound hitting times from above by mixing times. So th less than tg is easy. It's just like the proof you've seen before. So I'll focus now on the non-trivial direction. Which says that Tg, this mixing time when we stop at the geometric time, is less than a constant times this Th. Okay. Okay, so let's prove that. So let t be a time which is less than tg. So if we show that for any time less than tg, it's also less than th up to constant, then we're done. So that's the goal. And if t is less than tg, what does it tell us? It tells us that there exists some set A where, and there exists some starting point z where the probability at time t, starting from z, starting from z, the probability for the geometric of at mean t to be in A, this is less than pi of A minus a quarter. Okay, even strictly less. Okay, so this follows from the definition of total variation. Remember, before time tg, we know that the total variation distance between pi and this distribution is at least a quarter. So they differ. There is some set A where they differ on a quarter, by at least a quarter. Now, you might worry that maybe they differ the other way, that this probability is bigger than this one by a quarter instead of being less. But in that case, you just pass to the complement and you'll get the inequality as I stated it. So you can always ensure to get the inequality in this form for a suitable set A. Okay, so we have the set A, and now our goal is to find a set which has a large time to hit. Now, it turns out that won't be the same set A. We'll have to massage the set, get another set based on A, which will be hard to hit. And here, this idea of using geometric times will be crucial. I do have to tell you, one little story is when working on this problem back in June 2008, just relating mixing time to hitting time directly, I got stuck at some technical point, and So I consulted Oded during tea time, and he said, okay, remind me the definition of mixing time. I reminded him, and then he said, well, if you stop and if you run it until a geometric time or exponential time, then your technical difficulties should disappear. And it took me a few years to come back to that, but his suggestion was exactly right. And we'll see now how this geometric time will indeed remove all technical difficulties due to the lack of memory property of the geometric. So we have the set A. Now what is our goal? Our goal is to define a set. We'll call it B, which will have a large hitting time. And here is the set B. All the points Y, so that starting from Y, the probability at time ZT to be an A is large. It's bigger than, it's close to pi A. It's bigger than pi A minus 1/8. So this will be our set B that will take a long time to hit. And then the claim is that for theta small, for instance, theta which is 1/200 will work. The maximum over starting points of the hitting time of B is bigger than theta t. And remind you, t is any number less than tg. So once we get that, we are done, because we'll get that we'll have a set which is large, I should say, and pi of b is bigger than 1/8. So b is large. We need that for the definition of th. And it takes a long time to hit. Up to a constant, it's the same as tg, and then we'll be done. So we just have to substantiate these claims. We have plenty of time to do that. Any questions about notation or something else? All right. So let's prove these claims. And one of them will be immediate. That pi b is large because, well, most points have a large probability to fall in A. So let's formalize that. So pi of A, I claim, equals the sum over y, pi of y, py of x zt is an A. This just follows from stationarity of pi, because what is this saying? It says choose a point y according to pi and move forward zt steps. But zt is just a random variable completely independent of the chain. So if you start at stationarity, x at time zt is also stationary. So this is just saying, just taking the fact that pi equals pi p and averaging it. So this implies that pi is also, we take, so this is true, so this is pi p to the j, and now we average where j has this distribution zt, and we get this statement. Okay? So this is just easy consequence of stationarity. And now take this sum and decompose it into the sum over y in b and the sum over y in b complement of the same expression. Okay, now what can we say about each of these? So when y is in b, this probability we have no control. It might be very large. But so we'll just bound it by 1. So the first term will bound by pi of b. Now when y is in b complement, we know these probabilities are bounded by pi a minus 1/8, right? Look at the definition of B. So we can bound this by pi a minus 1/8 because this is bounded by that constant pi a minus 1/8, and then we add it with these weights, and these weights add up to less than 1. So just by, here I'm just bounding the pi of b complement by 1. So we have pi of b as a bound for the first term, pi of a minus 1/8 as a bound for the second term, and now just comparing the two sides, we get that indeed pi of b is at least 1/8. Okay, and here you can improve this a little bit, but this is good enough for us. All right, so the last thing we are left to prove is that the expected heating time of B from somewhere is large. So assume, in order to derive a contradiction, that the maximum over x Ex tau b is less than theta t. And remind you, t was defined up there. T was basically tg minus 1. Okay, so we're going to assume that and derive a contradiction. Okay, now what do we know? We know that starting from the special point z, the probability that x zt is in A, this probability is small. It's smaller than pi of A minus a quarter. Right? That's how the special point z was, and the time t was chosen. Question? Right, we know this. And this is certainly bigger than I'll write the conditional probability that x zt is in A, given that tau b is, okay, given that zt is bigger than tau b and tau b is less than m times t, multiplied by the probability of the condition. Okay, so, right, because of course if you multiply these probabilities, you'll get the probability of a sub-event of that. Okay, now comes the time where we can use the lack of memory property of the geometric. So how can we, let's look at the first term there. We're looking at the probability that x zt is in A, given these two things. Zt is bigger than the heating time of B, and the heating time of B is less than mt. Well, let's look at the chain at the heating time of B. So at that time, the chain is in some location in B, and we're conditioning that this stopping time Zt has not happened yet, because Zt is bigger than tau B. But if you condition a geometric variable to be bigger than something, then the remaining time is still a geometric with the same distribution. So that the first term, we can bound it from below by the minimum over all W in B, over all points W in B, of PW x zt is in A. So here is the crucial point where we use the geometric stopping, because we're saying this condition here won't matter, because we're going to stop at the time tau b. So here we know that this tau b happened before mt, but this doesn't matter. At time tau b, we use the strong Markov property of the chain. So the chain from time tau b will just continue normally. with its original distribution. So think of W as the location of the chain when it hit B. So this is some point in B. And the remaining time that we have, so ZT minus tau B, given that ZT is bigger than tau B, has the same distribution as the original ZT. That's a property of the exponential and the geometric distributions, this lack of memory property. That's very crucial here. And then the second, okay, so this is crucial for the first term. And then the second term will just bound by the probability that, so we'll want to make it that ZT is bigger than MT and tau B is less than MT. So note that this event here is a sub-event of this one. So this inequality certainly holds. But, okay, now, now this probability we can bound below by pi a minus 1/8 because of the definition of the set B. Now this probability here, these two events are independent because they involve different things. One involves the Markov chain, one involves ZT. Now a geometric variable with parameter t, the probability that it takes any value is less than 1 over t. So this probability here, right, we want to bound this from below. So this is at least 1 minus 1 over m. I mean, sorry, I'm saying ZT, what happened here? Okay. I need to, in all these inequalities, I want to add a theta. So, apologies. So everywhere here we'll add a theta. So it's just a change of notation. What I called m before, I'm putting theta m now. So, but everything is exactly the same. This will be just more convenient notation. And then we have, all right, so the first term can be bounded below by 1 minus theta m because the probability that ZT takes any value is at most 1 over t. So we're just excluding these mt theta values. So that gives us 1 minus theta m. And the last expression can be bounded by 1 minus 1 over m because we assumed that tau b has mean, which is at most theta t. So the probability that it's bigger than n times its mean is at most 1 over m. Is there a question? Okay, so the probability it's bounded by m theta t is at least this 1 minus 1 over m. So let's regroup. This follows from the definition of B. This follows from the property of the geometric, that the probability it takes any specific value is small, is at most 1 over t. And this follows just from the Markov inequality applied to the variable tau b. Its expectation is at most theta t, so the chance it's bigger than m theta t will be at most 1 over m. Okay? And now we're done, because if you compare these two sides, we'll get a contradiction just by choosing theta, which is of the form 1 over m squared, and m, which is large enough, for instance, 14. So if you choose theta, which is 1 over m squared, you'll just get 1 minus 1 over m, 1 minus 1 over m. And you already see that you get a contradiction for large m, because here we have pi a minus a quarter, and here we have pi a minus 1/8. So if this is replaced by 1 over m, this inequality is just impossible. And with these values, you get a contradiction. So the assumption failed. Okay, so any questions so far? Okay. So in the last 5 minutes will be more relaxed, and I just want to gives some intuition about these remaining quantities, especially this T stop is an especially fascinating quantity. And I want to tell you something about it. So let's look at, again, in the last, so if there are no questions here, I'll erase this and just in the last 5 minutes give you a couple of examples. Yeah. Yes? Yes, well, lack of memory, a distribution with lack of memory on the integers will be geometric. But, that's right. But to be honest, this proof can be made to work with other distributions, but it's smoothest with when you have a perfect lack of memory. And that, right, so the exponential distribution is what you would use if you're working in continuous time. Discrete time is geometric. Anything else? Okay, so I should say that this theorem has some, in terms of applications, heating times are, for a specific set, can be computed by solving linear equations, but of course we have here the maximum heating time over all large sets. Nevertheless, there are some applications, for instance, to robustness of mixing. Take any tree and change the weights on the edges, the conductances on the edges by a bounded amount, and show that the mixing time only changes by a bounded factor. This kind of robustness result we can derive from this theorem, but I don't know how to derive it from other properties of mixing time. So I'd say a general thing, about variational principles is often variational principles, sometimes they can be used to compute things, but often they're very useful to compare things. Okay, so this is another case of that. Now let me end with a few minutes on this stopping time. So I'll give a couple of examples of stationary times, and then so the plan is tomorrow I'll say a little bit more on the stationary times, and then turn to discuss cover time, where there is a connection to Gaussian processes and to Ofer Zeitouni's lectures from last week. So I won't assume you remember or understood anything from what he said, but at least it will bring some pleasant memories. So we will do that connection tomorrow, but now something about stationary times, and let's do a few examples. So again, a stationary time is a time where the chain has exactly the stationary distribution. One kind of trivial example is as follows. Pick a state at random according to the stationary distribution, run the random walk till you hit it. Okay? Of course, at that time, you're stationary because that's how you picked. This is rarely a useful stationary time. And this one is not a strong stationary time. So let me add a definition. So a strong stationary time S will have the property, it will be a stopping time, and also XS will be independent of S. Right, so XS, which is supposed to have law pi. So I remind you, stationary time just means that the probability that XS is in A equals pi of A. This is what it means to be a stationary time, and this should be true for all A. So that's a stationary time, but strong stationary time has the additional property that the stopping location is independent of the stopping time. The example I gave you is definitely not like that. Choose a state and wait till you hit it. If you know that you hit it very soon, then you know that it's probably near where you started. But let me give a couple of more examples, and then we're done. So one example is lazy random walk on the hypercube. So you have n bits. And the lazy walk on the hypercube works as follows. You choose a coordinate at random, and you refresh the bit there. So whatever bit is there, you erase and put a random bit, 0 or 1, equally likely. Okay? So this corresponds to simple random walk on the hypercube, but you make it lazy. So with probability half, nothing happens. With probability half, you flip a bit at a random location. Okay? Now, for this chain, there's a natural stationary time. Namely, you wait until you have touched all the coordinates. Okay? And at that time, all the locations have been randomized. And so at that time, the state is completely uniform. Now, how long does that take? Well, it's exactly the coupon collector problem, because we have to choose all n coordinates. So this takes time n log n. And this is indeed a bound for the mixing time. It turns out when you analyze the lazy hypercube more carefully, that the mixing time there is half n log n, and that there is a cutoff, so the mixing time has the same value, asymptotic value, half n log n, no matter what target epsilon you take. So for any choice of epsilon, T mix of epsilon is asymptotic to 1/2 n log n. This is a more precise thing than what I'm talking about now, but at least this stationary time, which is strong stationary time, easily allows you to get the bound of n log n. And again, I emphasize in this strong stationary time, when you have visited all coordinates, you're completely random, and it doesn't matter if I tell you how many steps it took to visit all the coordinates. It's still, even after that conditioning, you're still completely uniform. So it means it's a strong stationary time. And I'll finish with the very last example that I started with, the top 2 random shuffle. So we have n cards. Take the top card and put it in a random location. Okay, then again, take the top card, put it in a random location. And how long does that take to mix? Well, let's find the strong stationary time for that. So there is a very nice one. You wait till the bottom. So it's clear. I take the top card, put it in a random location every time. Wait till the bottom card rises to the top location, and then make one more step. Okay? So let the top card rise. So the bottom card starts at the bottom. It will eventually rise as cards are put under it. Okay? And it keeps rising until it reaches the top location, and then it will be the top card, and it will move to a random location. And that time is a strong stationary time. How do you see that? Well, look at what happens under this original bottom card. I claim that the cards that are going under that card are there in completely random order, completely uniform order. That is, if I wait till 2 cards are under this one, they could be in either order with the same probability. So this just keeps being true by induction. So by the time this originally bottom card has reached the top location, all the n minus cards under it are in a completely uniform random permutation. And then what do? We take this card and we put it in a random location. So now everything is completely uniform. So that's a strong stationary time. What's the expectation of this time? Well, how long till the bottom card will rise by 1? It's a geometric with parameter 1 over n. And then for it to rise again, it's a geometric with parameter 2 over n. And if you think about it, you'll again get the n log n for the expectation of this one. And for top 2 random, indeed, the mixing time turns out to be, again, concentrated at n log n. All right, so we're out of time for today, and we'll continue tomorrow on cover time.